So today's seminar is being presented by Dominic Jack. Dom is a research associate at the School of Computing and Information Systems at the University of Melbourne, working on graph neural network solutions to cybersecurity problems on a team led by Chris Leckie. He completed a Bachelor in Honors in Mathematics at QUT before returning to get his PhD from the Robotics Department right here in this lab, looking at deep learning approaches to 3D inference from monocular vision. He recently completed a COVID-interrupted internship at Microsoft Research in Cambridge in the UK, where he worked on a team attempting to leverage advances in reinforcement learning and gameplay to compiler optimization, before returning to Australia, where he took up his current position in Melbourne. All right, Dom, would you like to take it away?
Thank you very much, Dorian. Graph and spectral graph theory. Now that's a bit of a mouthful, so let's just break that title down step by step. So by graphs, I'm talking about networks of graphs, interconnected nodes, nodes and edges, vertices and links. I'll use those terms interchangeably. I'm not talking about XY coordinates joined up by lines. So hopefully we've all had some experience of graphs before. If not, I've got some examples coming up and it will be fairly apparent that you have used them before, even if you haven't used the correct or the formal terminology. I'm not expecting you guys to have a massive understanding of graph theory or have done a course or anything, but just understanding the general structure is important. We're looking at applications in neural networks. Again, I'm not expecting everyone to be an expert in neural networks, but a basic understanding of neural networks would be great. If you know what a fully connected layer is, you know what an image convolution is, then that's a good start. And that's pretty much all you'll need to understand this talk. And lastly, we're talking about spectral graph theory. That's obviously related to graph theory in general. It does involve a little bit of linear algebra. If I say AX equals lambda x and you think eigenvalues, then that's probably all you need to know. As well as maybe if you have a special matrix A, you can decompose it into V lambda V transpose, where V is a matrix of eigenvectors and lambda is a diagonal matrix of eigenvalues. So that's about all linear algebra you really need to know. This talk isn't so much about high level or low level details and implementations. We don't go deep into any one of these topics, but we're just going to try and mesh them together and give you guys an idea, an intuitive idea of how it all works. If you do have any questions throughout, feel free to either shove them into the chat. I'm not keeping an eye on the actual audience, so Dorian, if you want to shout if there's any hands up there. But I am happy to answer things as they come along. Otherwise, there should be a few minutes at the end for questions. All right, so before we get started, let's talk about some motivating examples. So might start from the top right and go down around. This top right one is the one you're probably most used to when we talk about networks, and that is the social networks. So it might be your set of Facebook accounts and the friendships between them. In that case, the accounts are the nodes and the friendships are the edges. And we want to be able to learn things from a partially completed graph or the graph, which may have nodes which we don't know much about. So if your friends all like basketball, do you like basketball? That's the sort of questions we would like to solve. Or given how many of your friends like basketball and how many of those friends like basketball, how does that influence your liking of basketball? That's the typical social network type problem. Just below that, we've got a sort of CAD mesh of a fighter jet. So a mesh is a type of graph. You have vertices and edges. You also have higher level constructs like faces, but from the perspective of the graph, we just have the vertices and the edges. And you might be interested in, say, classifying each of those vertices. Is this vertex associated with the wing, or is it associated with the cockpit, or is it associated with the tail? Those sorts of problems. Below that, we have a chemical or a molecule with individual atoms and the bonds between them. That's a really good graph problem. The graph structure is apparent just by how we normally represent them. again, the atoms are the nodes and the edges are the chemical or the atomic bonds between different atoms. And the sort of question we might be asking, is this particular molecule soluble in water? Right, and given the data set of lots of different molecules, we might try and work out what properties of the structure lead to properties that we can observe in the real world. Down the bottom here, this big world map can represent sort of any number of graphs, either like transport networks, supply chain problems, computer networks, all very important in different areas. If you want to know how to get from A to B, every time you've tried to book an international flight where there's not a direct flight, right, there's been a graph problem that's been solved at some point. Yeah. And finally, this top guy here doesn't look too much like a graph, ax squared plus bx plus c, but we can think of any mathematical expression, or more generally any computer program, as some abstract syntax tree, which makes up. So A, X, 2, B, and C would all be sort of leaf nodes, right? And this ax squared term is made up of a product of A and x squared, where x squared is a power of x and 2. Right, so we can break those down. So all these are examples of graph problems, and there are lots and lots more. All image problems are at a high level graph problems, right? Where each pixel is generally associated with its nearest neighbors. Right? You can have like the 8 and 8 pixels around it as the edges, or you could just use 4. And there's lots of ways of representing image problems as graph problems. Even text problems can be thought of as graph problems, right? Where each word is connected to all of the previous words. So we've done some work on transformer and natural language processes, and that's kind of what they do with that. Just a quick story about my journey with graphs. So I did a PhD at the very department that you're all at, and I was in computer vision problems. So I started with just regular old image convolutional neural networks, and at some point I wanted to be doing things with graphs, with point clouds, and I wanted the point cloud convolutions to feel like image convolutions, or at least be mathematically similar. So I did some hacking away and some algebra, and in the end, all it really boils down to is doing some neighborhood search and then adding up stuff for other points in a neighborhood. Right? Another way of looking at it, though, is we create a graph based on that neighborhood lookup, and then just use a graph neural network. Right? It's almost exactly the same. After I finished my PhD, I went over to Microsoft, where I had a spectacular day in the office. So day one, I got to see the baby grand in the foyer and where all the good coffee places are. And day two, I got sent home to work remotely. So it was a long way to go for one day at the office, but still finished the program remotely, so that was okay. The project I was working on is a really good example of graph networks because, or the graph applications rather, because there were 2 graph applications in one. We were looking at compiler optimization. So if I give you a program, say that this top left, this 2 plus x plus 3, oops, how can we compile that? Can we get a better representation? I hope we can all agree, just looking at that we could probably write that as x plus 5. And at runtime, x plus 5 will have 1 fewer floating point operations than 2 plus x plus 3. But the question of how we get there, if you really want to break it down, is a bit like a graph search. Right? So we could commute the 2 plus x to get an x plus 2, and then we could use the associative property of this to put the brackets over here, and then we could simplify the 2 plus 3 to get our x plus 5. That's not the only thing we could do. We could also, use association first, or associativity first rather, and go over here, but that's a bit of a longer path to get to where we want. So at high level, we have a graph search problem, right? And it's an infeasibly large problem. You can't just do sort of brute force and look at all possible rewrites. This is a very, very simple program, right? And even that one gets fairly big, and we haven't tried to add all the possible rewrites we could do. And then each node of this graph is itself a graph, right? 2 plus x plus 3 is a mathematical expression, or more generally, we're looking at computational programs. So the question is, how do we get a good idea of how good this expression is? Well, we use neural networks, or graph neural networks specifically, to evaluate the graph made up by the abstract syntax tree there. Now, there are lots of different problem types in graph neural networks. I'm only going to be discussing a very small subset of those, but most of the ideas we talk about here apply to the other areas as well. So formally, we're given a set of nodes and edges, right? Or you could say vertices and links. I generally prefer nodes and edges, but they all mean the same thing, right? And the nodes may have associated features. So if we think about our social network thing, your account has certain properties based on what you like and what you don't like, right? That's in addition to who you're friends with and who you're not friends with. They're the edges, whereas whether or not you like basketball is a feature associated with you. Now, edges may be directed or undirected, right? So something like Facebook is an undirected graph because if I'm friends with you, then you aren't necessarily friends with me. Twitter, on the other hand, is a directed graph because I can follow you without you following me. Right. Typical tasks include graph classification or regression. So if you think about the question of, is this molecule soluble? That's a graph classification problem. Soluble in water. We're trying to get a property of an entire graph based on the structure and the node properties. But there are other things we can do. Edge prediction or regression is one you would have seen. Again, the social network problem. If you've ever had a friend suggestion pop up, that's the result of an edge prediction algorithm. Right? So there's not an edge there right now. They're not going to suggest you make friends with someone if you're already friends with them. Right? But based on your mutual friends and your likes and their likes, some algorithm has decided that there's a good chance that you are actually friends with them in real life. And the last problem is the node classification or regression problem. Like, do you like a thing you haven't specified that you like? Do you like basketball? Do you like apples? At a higher level, we have inductive versus transductive learning. Now, those words have very specific technical meanings, but in this context, it generally means inductive problems have many disjoint graphs and an unknown set of test graphs. So the question of molecular solubility is a good example. I'm going to give you 1,000 molecules, and I'm going to tell you whether or not each one of those is soluble in water. And then at test time, I'll give you another 100 you've never seen before and ask you whether those are soluble. Yeah. Transductive tasks, on the other hand, have one graph, right, and some labeled nodes. So if we look at this graph here, maybe we know lots about these 4 people because we've gone and paid them some money to give us lots of data about them. And we try and use that data to infer similar properties about all the unlabeled people. Another really good example of this is botnet detection. So detecting fake accounts on, say, Twitter. At one point, I think Twitter deleted about 1/3 of its users because they decided that they were all bots. Now, you can't go through and manually classify each account as bot or not bot. You might want to try and manually classify, say, 0.1% of accounts, and then have an algorithm go away and automatically classify the rest based on patterns it detects in that very, very small subset of labeled examples. Now, the rest of this talk is going to focus on the undirected transductive tasks, but a lot of the ideas have analogies or have corresponding things in the other problems as well. All right, so before we get into some algebra, and I promise it's not too much algebra, right, it's a couple of really important matrices that we use to discuss graphs. The most obvious one is the adjacency matrix, right? So this graph up here is one that we'll be using a fair bit to demonstrate some examples. Right, we've got this ring over here with one cross edge and another ring over here, and a few cross edges in the middle. Right, and our adjacency matrix just has a 1 everywhere there's an edge, or the weight more specifically everywhere there's an edge, and 0 otherwise. All of these problems, there's no natural weighting associated with them, so we just use 1 if there's no natural weighting, but sometimes you will have weights associated with things. So if you look at this adjacency matrix, with enough practice, you get to recognize structures. All right, this chunk down here, this is the adjacency matrix associated with this ring. All right, one's on sort of the off diagonals, and another one, a couple of ones in the corners. There's a similar ring-like structure up here. It just has an extra 1 here, given by this edge. All right, and then these 3 cross edges are in the off diagonal blocks. Right, so that's our adjacency matrix. Our diagonal matrix is just a degree matrix is a diagonal matrix with entries given by the row sums. Right, so A has 2 edges, right? It's connected to 1 and 4, right? So there's a 2, right, corresponding to the number of edges going out of node 0. We look at another one, say 6. 6 is connected to 5, 2, 3, and 7. So there should be a 4 in there somewhere. So there are 2 fundamental matrices, and we can, I guess, only our adjacency matrix is the fundamental matrix, and D is derived from that, but we use them enough that we give them special measures. All right, so we'll talk about some spectral intuition. And whenever I say spectral, if that scares you, just think eigenvalues and eigenvectors, or the properties of those. So a problem that you might have encountered, I'm not sure what engineering students do or what your background is, but maths, at least we can count but lots, is the problem of diffusion. So let's try and model heat diffusing over, say, a board, or chemicals diffusing in water based on spill, in this case, at these 2 locations. Well, if we represent the temperature or the concentration in a flattened array, right, then we can step this in time, right, using this equation down here. Now it looks a bit scary, right? This gamma just represents like a constant. It's like the change, the time step. But mostly we have A times U, right, which looks like for each pixel, we receive some heat from the surrounding pixels, right? And minus our D times U, that's the amount of heat we lose to the surrounding pixels. Right. So that's one common example of a graph problem. Obviously, this is on a regular image grid, this picture, but you could do it on some warped surface with holes in it. Another problem that you have used the solution to plenty of times is what we call sort of random walk or personalized page rank. The name page rank comes from Larry Page, i.e. the guy who started Google. So if you've Googled something, you've probably used something like personalized page rank. Nowadays, it's much more complex than this, but this was the original sort of idea. And intuitively, the idea is we start at a given node, right? Say we start at 0, and we just randomly take one of the outgoing edges, right? And then we repeat that process over and over and over again. And we try and model our probability of being at any node at a given point in time. Now, we don't actually simulate these things, right? Because that takes a long time. It's much better to do it with sort of matrix algebra. And it looks like this. Now, the one thing I haven't explained is if we do this over and over again for an infinite number of steps, then you will find that any node that's connected to any other node has the same probability of being landed on. Sure, if you start here, initially you'll be more likely to stay over here, but over an infinite time horizon, you'll eventually be over here just as often as you are down here. We have this little restart probability epsilon. They say with probability epsilon, we're going to go back to node 0. That's what the green flashes represent, right? And with probability 1 minus epsilon, we're going to take a random step in any other direction. And you know, here's some maths. You can go away and convince yourself that that's correct if you really want. But it's not all that important. The key takeaway I want you to look at is these D minus A like structures. So I know we've got this 1 minus epsilon here, but epsilon's normally pretty small, maybe like 0.1. So it's essentially a D minus A. Right, and over here you have an A minus D, which is just a negative D minus A. Right, it turns out these D minus A or A minus D structures pop up quite a lot in graph problems. So much so that it's got its own name, and it's called the Graph Laplacian. Right, so it's D minus A. Right, and Laplacian, that's a scary sounding name, but it's really not too bad. It looks a lot like the adjacency matrix, just with the -1 where there was a 1 beforehand, right? And the D set up such that the rows add up to 0. Right, and that's all it is. If we do that, then our equations from the previous page look arguably nicer. Right? And yeah, so that's the motivation for these Laplacian things. All right, so that was the motivation for looking at these Laplacians. Let's look at the motivation for looking at the spectral features, or eigenvalues or eigenvectors. All right, well, recall this Laplacian thing is kind of like diffusion, right? So if we have a graph like this, so they're two separate components of the same graph, and we just diffuse things over and over and over and over and over again, right? We're going to end up with everything the same temperature in this component and everything the same temperature in this component. And they won't necessarily be the same because there's no sort of heat, no way from heat to pass from this component over this component, right? So they'll be different, all right? But they will be the same over the same component. So if we look at this first eigenvector, sorry, the eigenvector associated with the smallest eigenvalue, we get these sort of uniform values across the connected components. And hopefully that's not radically surprising if we think about it from the perspective of diffusion. Similarly, if we look at the next eigenvector, or the eigenvector associated with the next smallest eigenvalue, we get the same thing. In fact, both of these vectors have an eigenvalue associated of 0. And I'm sure you can imagine if you add more connected components, then they've got an extra eigenvector, right, with the slightly different constant values. But the point is that they'll have the same eigenvalue of 0. And again, from the perspective of diffusion, hopefully that's not too uncomfortable for us all. We're just multiplying by this L lots and lots of times, which results in this diffusion operation, right? So we end up with very diffuse temperatures. But at the same time, if we forget about diffusion and we just think about spectral features, right, and spectral values, we've solved a sort of very discrete kind of problem, like what are the connected components of this graph, or how many connected components are there in this graph, using these spectral features, right? Turns out that if you just count the multiplicity of the 0 eigenvalue, you can find how many linearly independent eigenvalues have, sorry, how many linearly independent eigenvectors have eigenvalues of 0, right? Then you have the number of connected components, right? And we never looked at sort of graph theory problems of finding connected components, right? We just did some eigenvector and eigenvalue analysis of our Laplacian matrix. Right? Now, admittedly, that is a very expensive way of computing the number of connected components, right? But the really cool thing is, if we don't have this discrete separation, right, of the connected components, we still see similar things. So if we go back to our original graph that was all connected, so we add these 3 edges back in, our first eigenvector still is uniformly diffuse. Right, again, that just comes from diffusing over a fully connected component. But our next eigenvector has this really nice property where it's kind of separated out from this ring to this ring, right? If you look at this, these guys might be near 0 and these guys might be near 1, or vice versa. Right, and there's this smooth transition from one to the other. Just for the record, this isn't me plotting down lots of circles and joining them up and just choosing colors that are good. These are literally the color map values associated with the eigenvalues of this graph. Right, so if you wanted to separate this ring from this ring, you might put a threshold value of, say, 0.5, and maybe all of these guys have a value less than 0.5, all of these have a value greater than 0.5. Right, so that kind of agrees with our own intuitive understanding of the clusters in this graph. We can't talk about connected components, but there's clearly a structure-y thing over here, and there's clearly a structure-y thing over here. And the first, the eigenvector associated with the first non-zero eigenvalue gives us that. Now, that's a very, very rough, high-level motivation for using spectral features. But it turns out there's lots of really cool stuff that you can do with spectral features. Things like graph cuts. How many edges do you need to cut to minimally separate a graph into two things? You can have very strict bounds on that value based on the eigenvectors and eigenvalues. I'm not going to go into that here because we don't really have the time. But the point is, these questions that we often want to solve in graph theory, like classical graph theory, we can get very good bounds on by looking at the eigenvalues and eigenvectors of the Laplacian matrix. Right. So just to summarize, right, I'm not going to try and prove all of these, but hopefully that intuitive understanding gives you a good idea. Right. The eigenvectors with the associated eigenvalue 0 identify our connected components. Right? Our eigenvectors with small associated eigenvalues, but non-zero, they provide good node features for clustering or other high-level tasks. And there's much, much more. Right? And these properties are mostly the same for the symmetric normalized Laplacian, right? Which just looks like our L, our normal Laplacian matrix pre and post multiplied by d to the minus half. Right? Which we'll often also write as I minus a hat. Few sort of things that are nice to know about spectral features. Just like our normal Laplacian, our lowest value is 0, and all of our eigenvalues are between 0 and 2. Over here, we just have an example of spectral clustering based on just those eigenvectors. So we start off with the mesh, right? We perform the eigen decomposition, and then we do k-means clustering based on the coordinates in the eigenspace. Right? And so this isn't a supervised learning task, but clearly it's identified structures like the palm and each one of the fingers. It's pretty cool if you ask me. All right, I'm running a little bit slow, and I know we all want to get lunch, so I might speed things up just a little bit. Still seeing no questions, so I'm just going to keep on going through. So let's talk about graph convolutions. So we said earlier, our Laplacian looks like our normalized Laplacian looks like our identity minus our normalized adjacency matrix, right? And we can break that down into our V lambda V transpose just by doing an eigen decomposition, right? Where lambda here is our diagonal matrix of our eigenvalues. We said that the small eigenvalues associated with lambda are important. Right? We want to do stuff with the eigenvectors associated with small eigenvalues, right? But we also want to learn things because deep learning is a big craze and it's been doing really good things in image processing. So how can we learn things? Well, the idea of spectral convolutions is we do some learning on these eigenvalues, right? So we learn some mapping F, which transforms each of our eigenvalues independently, right? And we're hoping that it's gonna make our small eigenvalues big, so it amplifies the effect of those small eigenvalues, which we know, or intuitively we think are important for high level tasks. And hopefully it shrinks down the less important ones, those eigenvalues near 2. Now there's some problems with this. Our V is n by n, right? That's big, but like the Facebook graph, there might be like a billion accounts. So n is a billion. You don't want to be, creating a dense billion by a billion matrix, which is what this V matrix is. Right? So we want to be a little bit smarter in what our F is, right? So what happens if we use our F to look like some learned parameter times 1 minus lambda? Right, so 1 minus lambda, that's going to amplify our eigenvectors near, our eigenvalues close to 0. It also amplifies our eigenvalues close to 2, so it's not ideal, but let's just see what happens. Well, if you do that and you sub it in, right, and we just move our theta out to the right, we end up with something like this, right? And this V, I minus lambda V transpose, turns out is just our normalized adjacency matrix. Right? We can also get rid of the summation over I and just write that in matrix form rather than vector form. And we end up with our expression for this expression down here. Now this down here is what we normally call spatial convolution, right? And the reason for that is on the next slide. So if you think about image convolutions, each one of our pixels ends up being the result of a sum over our neighboring pixels, right? And there's some scaling by learned parameters, and, but that's how it works, right? Well, a spatial convolution works in exactly the same way, right? This A times X is just an addition over all of our neighbors, right? Scaled, right, by some normalized weight, right? But it's still adding up things from our different pixels, right? And then our X times our theta is just some learned linear transformation. Right? As it turns out, you can do these in any order you want, right? Multiplication or matrix multiplication is associative. So you can sort of do some neighborhood aggregation with A times X, and then you can transform your features, or you can transform your features, then do neighborhood accumulation. It doesn't matter. You should get the same results in a perfect floating point environment. In a perfect mathematical environment. So our spatial convolution kind of agrees with our concept of image convolutions. Right. So to generalize, we also have these message passing networks. Oh, I should just say quickly, this is also nice and easy to implement, right? Because our A times X, A is sparse, right? So A times X doesn't involve creating any large n by n dense matrices. So to generalize, we have these message passing networks, which are made up just by alternating learned transformations and propagations. Now, the propagations in the previous thing were just A times X, right? There are some variations on that. Sometimes we do sort of max pooling over neighborhoods rather than sort of weighted sum pooling. But we have some way of propagating information between nodes, and then we have learned transformations. So this AX theta is an example of one of each, right? We have the learned transformation and the propagation. Right, now, if you've done some neural network stuff, you know that you can sort of add nonlinearities in there. You can make the, yeah, I guess I'll just go through the dot points. So you can make the receptive field larger by adding more propagation layers, right? So just adding more and more of these things, right? Or increasing the receptive field of each propagation operation, right? So for instance, rather than using a normalized A, you could use a normalized A squared or A cubed, and then you'll get like the 2-hop neighborhood or the 3-hop neighborhood. And conceptually, that's kind of similar to using bigger filter sizes in bigger convolutional kernels in image convolutions. Right. Now, our model capacity can be increased by increasing the capacity of each learned transformation. So previously, we just had a linear transformation, right? Presumably there'll be a nonlinearity in there somewhere, but you can have 2 or 3 linear transformations separated by a nonlinearity for each learned transformation. Right. So some work I've been looking at is what I'm calling a Resnet-Inspired propagation. Right. So what happens if we take this idea we were discussing previously of getting high capacity learned transformations and high receptive field propagation operations. Right. We're going to take that to the extreme. We're just going to do a nice big nonlinear node-wise transformation at the beginning, right? So that doesn't take into account any of the adjacency information, none of the edges. And then we're going to do a deep propagation, right, which is only going to look at the edge information, right? It's not going to look at any of the node features other than to propagate them around. And the deep propagation that I'm going to use is a Resnet-inspired propagation. So by Resnet, I just mean I'm going to put lots of these residual skip connections in and just do a normal propagation of multiplication by A. Well, here's some algebra that I don't really want to go through, right? Because I am conscious of the time. But if we do this, right, it doesn't actually converge if we use our normal adjacency matrix. But if we put this small decay factor in, then it does converge, right? So if we look at an infinite number, look at this guy here, but projected infinitely, so we have an infinite number of these projection operations and skip connections, right? So long as we add in this small epsilon or 1 minus epsilon factor, right, then this summation converges to an inverse problem, right? I'm calling this whole operand here just L epsilon, as in it's a slightly shifted normalized Laplacian matrix. So that's some cool algebra, but do we have any sort of reason to believe it might be good, other than ResNet's kind of good? But before we get to that, let's just think about some different interpretations, right? The interpretation I've just talked about is the skip connected propagation, right? So if rather than just doing a single propagation, we propagate decay, skip connection, propagate decay, skip connection, propagate decay, skip connection, then this is the representation we get. But there's also a cool spectral interpretation, right? If we go back to this form of our spectral convolution, and rather than our f being 1 minus lambda with a theta, we do a 1 over lambda with some shifts to avoid singularities, right? Then we end up with this expression up here, right? And recall we said that eigenvalues near 0 were important. Well, this is going to bump up the eigenvalues near 0 quite a bit, depending on how small epsilon is. And unlike our normal graph convolution, it's not going to also amplify the eigenvalues near 2, right? Because 1 minus lambda will amplify those, right? But we just get nice decaying of eigenvalues that we don't care about. Right. The other way we can interpret it is like a tweaked page rank. This is the formula for tweaked page rank. So this is the formula for the original PageRank. The only thing we've got different is rather than D inverse A, we've got a symmetrically normalized A. So a D to the minus a half, A D to the minus a half. I also got this epsilon out the front, but that's just a scaling factor. So not too fast. So it's kind of nice that all of these things come back and like loop around and have similar interpretations. Now, of course, if we do this, right, we still have this inverse system to solve, right? And how do we solve that system? Well, you can use Taylor series, right? Just go back to this interpretation down here, right? And that works, but it's not particularly efficient, particularly from a deep learning perspective. You have to store in memory each one of your terms in order to backprop through it. And there are much more efficient ways of solving linear systems, right? If the most efficient way of solving a linear system was Taylor series, then linear algebra courses would be a lot faster. All right. So lots of other things you can use conjugate gradient, right? This has various nice things that you can that work well in deep learning processes. Low rank approximations can make it a lot faster. You can pre-process the first, say, 5 eigenvectors and eigenvalues. And other things you can do is pre-process certain rows and columns of this to make it better for certain training sets. That's all I've really got to say. The only other thing I will mention is that I've really only touched on all of these concepts. If you're interested in more spectral graph theory, Daniel Spielman has some really good lecture notes available, and there's a really good YouTube video. I strongly encourage you, if you're interested, to check out his stuff. That's just the spectral graph theory stuff. There's also a whole machine learning course available if you're looking at the machine learning stuff specifically, and there's a whole bunch of packages available as well. I have gone slightly over time. Hopefully you'll forgive me, but if there's any questions, I'm happy to stick around and answer those.
Right, if folks want to put up their hands and mute their mics, thank you very much, Dom, by the way, for an excellent presentation. Questions, James? Question on that spectral feature stuff. That was really, really cool, by the way, especially with the hand segmentation in the mesh. Have you used that sort of stuff in your current work at the University of Melbourne?
No. So the idea is I've looked at. So the idea of this is we get the features, yep, right, and then we forget all about the connectedness, right? We just have, so if you have, say, 10,000 vertices, right, you might take the first 10 eigenvectors, right, and so each node of this now has 10 features associated with it, and then you can do k-nearest neighbors clustering on that. So that's just like a higher level task. It's because I'm looking at deep learning stuff. I'm saying, well, rather than using k-nearest neighbors, let's put something else in there, right? And more so than that, rather than actually computing these eigenvectors, because that could be, performing the eigen decomposition can be expensive, can we do operations with the sparse adjacency matrix rather than that? But yeah, there's certainly a whole heap of people doing really cool stuff with just spectral clustering, so no learned stuff. Just saying, hey, look, these guys are probably similar, and hey, look, the eigen features are close together.
Very nice. Got a question from your old supervisor there, Dom.
Frederick, what do you do when the structure of the graph is not static? Well, you panic, Frederick. Yes, there's the graph problems are varied, and dynamic graphs are probably much more common in a lot of application areas like neural networks, social networks, for instance. There are constantly new friendships being created. If, for instance, you need to do an eigen decomposition, you don't want to redo that eigen decomposition every single time a new friendship is made on Facebook. I haven't really done much stuff on that myself, but yes, dynamic graphs are a whole different problem. They still involve mostly this idea of propagation, but implementing that propagation isn't as simple as just doing an adjacency matrix times an x. So we have these edgewise, I don't want to say discretizations, but breaking that propagation down into individual edge propagations. But it is very much an open problem and very interesting.
Nice.
Sorry. Another question. Dorian has the slides. If he's right, Mustafizer. Sorry, I probably butchered that one.
I can distribute them.
Feel free to do with them as you will.
Right. David Lovell has a question. David, go ahead.
Great to see you, Dominic. Thanks for a lovely presentation. Can you, like, building on Frederick's question, can you just comment on taking information that has been learned on one graph structure and using that information on another graph structure? It's not quite the same as what Frederick sort of said when, you know,
No.
we recognize the graph is dynamic, but it is about, you know, this issue of, you know, learning something from one domain and bringing it to another. Is that a thing? Can you talk about that?
Yeah, so that's the inductive problem.
Yeah, cool.
So it's definitely a commonly used thing. You have to be a little bit careful with spectral convolutions if you do something like this, because your eigen decomposition is going to come back in maybe different orders, like based on the graph. You know, you can make a small change. Then if your eigenvalues are very close, then the eigenvectors associated with the same concept can be in different orders. But spatial convolutions do very well. Right, these just have an a times an x. So, you know, if you think about the diffusive idea, then you just don't diffuse over certain edges if there's slight changes to the graph.
Cool.
I would have to look more at exactly how you could do this. My gut feeling says this still works a little bit, because if you change, I stand to be correct. I think this still works. I originally implemented this f of lambda theta as just theta, and that does not work, right? Because of that changing slight change in order. Sometimes that happens. But if they change in order, then they change in the column of this. There's a switch here, and there's also a switch over here, if that makes sense. So long as you have a continuous function of lambda. Like,
yeah,
my recollection of it is it works.
Thanks, Tom.
All right. I think that's all the time we have for today. So everyone, please give big thanks to Dom for an excellent presentation.
Thank you very much.